So let's calculate the surface area of a cone. In the first case, we will consider the curved surface area and then we'll go to the total surface area. And just as a quick reminder, curved surface area, if you take this cone, curved surface area is just the area on the side, the lateral side areas, whatever it is over here. Okay, we are not going to take the area of the base. Okay, we assume that the area of the base is open. There's nothing, it's not closed, it's open. So whatever remains on the curved side, that is the curved surface area, and that's what we're going to talk about. Okay, and just what I've done is I've copied some visuals from this particular website, and you can check out. I've got given the link. It's the same website, but what they've done is they have used all this sequencing in the animation format. So you'll see actually how this is opening up. Okay, and what we're trying to do here in essence is we're trying to unwrap the cone or open up the cone. So we have a cone here. Let me get rid of my doodles here. So let's say we have a cone here, okay, with the bottom is open. Like assume that it's a waffle of the ice cream, the bottom waffle of the ice cream with no ice cream, okay, with no ice cream. So it will be like open on the top with that, okay. So let's say we have that and we slowly open that up. So what does happen? We are slightly cutting it out, and there's a slow animation of that, what happens all the way through. So this comes out, this part comes out. There is no a circular force, but this part comes out, and slowly this opens up, and this opens up. And if you see finally what happens, if I make this visual bigger, what happens is focus on the green portion. The green portion is nothing but a sector of a circle. Okay, if I would have completed this completely like this, it would have formed a full circle, but now the way it is cut out, it is just a portion of the circle, as if I have cut out this portion completely from the circle. This portion is cut out from the circle and just a sector is left. That's what it looks like. And if you again notice in this diagram, see this green line is getting carried out. So the green line is nothing but, if you had a complete circle this way, this green line would have been the radius. Green line would have been the radius of the bigger circle or the imaginary circle. So this way, because this is a center point, and this would have been the radius of this whole circle. And at the bottom also, let's say if you had a circle, or even if you don't have a closed circle, it's open at the bottom, but still when you complete the cone in this format, this still forms a circular base shape. Okay, it's not closed, but it forms a circular base, and this base also has a small radius by itself. If you measure it from the center of that base itself, and this orange line is kind of capturing that particular piece of the smaller radius. This is also a radius of the smaller circle at the base. So, and since we're going to talk about the curved surface area, we will not count that this is existing. We'll not count this. We'll just talk about this because this is open right at the bottom. Okay, we will use this radius for calculation, but we will not add up this area on this. We'll ignore this area of this bottom circle, and we will use that in the total surface area. So that's how it is. Okay, so now we'll just focus on this concept of the area of the circle and the whole overall area and this area of this sector, and then we'll see how to calculate the surface area. So as long as I calculate the area of this green portion, because this is what the cone was originally about, this green portion, this whole green is now opened up. As long as I calculate the area of this green portion precisely, that will be giving me the lateral or the curved surface area of this cone, because this and this are the same in terms of the animation. So that's kind of the context. Now let's see what we have. There was a nice way that I copied from one of the internet sites that put it. I forgot the link of that. I'll try to add it. This explains everything. So you have a circle here, a big circle. Remember the imaginary circle I told you over here? I was trying to imagine a circle for you on the green portion. So assume that this circle we are talking about. So we have that circle here, and a portion of that is cut so that we have only the green portion, which is a big sector or a big arc, whatever is remaining here. So if you see this only portion is remaining because the other portion is cut out. So assume that that's the imagination. So this is the remaining piece, and we're going to focus on this piece. Okay, but you can imagine that there's a full circle completed with the dotted lines. Okay, so what's happening here is, this is the cone. Okay, this is the cone with the open base, and if you see, there are things that are very self-explanatory. I'm going to unwrap or open it. Unwrap means opening it. Okay, but while I open it, just see what's happening here. This is a cone, And from this point to the center of this base, that means this center, if you see this is the height of the cone. Okay, this is a straight height. So whenever we talk about the height of the cone, we have to just imagine this portion. If it was within a cylinder, it would have been the cylinder portion. For example, if this cone is inside a cylinder, we're talking about this height here. Okay, if this cone was inside a cylinder like this. Okay, and this was the cone base. Okay, this is the height we're talking about, and this is the radius. This radius is this radius of the bottom circle, but there is no, it's not closed, it's open, but it will still have a radius because it forms a kind of a circle. Assume that you are wearing a birthday hat. Okay, this looks like a birthday cap. It looks like a birthday cap, right? So it will still have a circular shape at the bottom with this kind of a radius. This is what we talked about here, this orange line. Okay, this is a small radius, small circle, or whatever that is. Okay, and those will be perpendicular. This if you connect this dot all the way to the height, which is this height here, they're going to be perpendicular. And from this vertex, if I join this point, I'm going to get L, and L is nothing but, it's a terminology called as slant height. Okay, there are two heights in the cone. If I just use the word height, I'm talking about this height, which is exactly perpendicular from the vertex to the center of the imaginary circle or the smaller circle. If I'm going to talk about slant height, then it's going to be this height, which is a slant, which is nothing but this portion over here, this green line, the radius of the bigger imaginary circle. That's what this is all about. This is a slant height, but when I open it, we already discussed that this is going to be the radius of the bigger imaginary circle. Okay, so what's happening in essence is the radius of the bigger circle, since in this context, in the right angle context, it forms a hypotenuse. I can apply the Pythagoras, and this will become the hypotenuse. So I can say L square is equal to R square plus H square, which is nothing but the radius of the base plus the vertical height. And then I'll get this formula, which is under the square root. So basically, in essence, what we have done is, in this calculation, it also covers the radius of the circle at the base, and L slant height is nothing but the radius of the bigger circle, which is imaginary at the top, right? In the sector, the green line. Okay, so it has a green line also. So the same formula kind of has both the radii of a smaller and the bigger circle. Now let's try to unwrap that, like we did in the animation above, when we're trying to unwrap this completely from left to right here. So let's try to unwrap it. Okay, when we unwrap it, we will not get a full circle because it's a major sector and this portion is gone, right? Let me use a different color. So let's say this orange portion that I'm drawing, this portion is not there. Okay, we have to just imagine when we complete this dot, it completes the full circle, like I've shown you at the bottom, up at the top where I'm putting it in dot. So that's the full circle. So that portion is gone. So I'm putting it in dot so that you can imagine it forms a full circle. But when I open up the cone, this is not there. So only the green portion is there. So let's do that. So what do we see here? Okay, and this diagram over here is nothing but a side view from looking at the bottom, where we see this also forms a mini circle, but it's open, right? It's not closed because we are talking about the lateral surface area where the bottom is open. So this also forms a radii in that context of a circle. Okay, now what happens is we'll apply the formula that we learned from the area of a circle proportional to the sector length. We'll apply that because what we are going to see here is, let's look at here. The area of the green sector is what we're trying to calculate. This area of the green sector is nothing but the surface area, because when you open up this cone, all that is remaining is this green area. Okay, that I'm highlighting in purple color. That's interesting. Okay, so we're calculating this area, that is the surface area of the right circular cone. So this area, and this is nothing but a sector, the whole green portion that is highlighted, that is an area of the green sector. That's what is written here. And that is going to be proportional to the length of the green arc. That means from here, this arc, which is I would not call it a circumference because the circle is not complete, but almost whatever is there up as a part of that particular sector, this whole length, like assume that if you open up, this is going to be like a rope from this point to this point, a big rope, right, of this length from here to here. If you straighten it up, this is going to be a big rope. That's called as the length of the arc, or the length of the green arc. So areas will be always proportional to the length, because we have seen in the last episode that area is going to be proportional to the circumference. But in this case, it's a sector, so it's not a whole circumference, but the arc length. And at the bottom, we are going to get the area of the whole circle. And what is the area of the whole circle? If I remove all this, Okay, if I'm removing all of this, assume that I connect the dots here and complete this circle. Okay, this area of the whole circle, the ratio I'm taking at the bottom is going to be equal to the circumference of this whole circle. Assume that if this whole circle was there, the ratio would have been equal. So what are we talking about? The ratio is going to be the same. What is the ratio we're talking about? Ratio of two areas, area 1 and area 2, is going to be equal to length, respective length of that sector versus length of this sector, and at the bottom we have a whole circle. Okay, that's the fundamental, and you can check out my previous topic on the area of the sector. We are going to use that formula here. I've derived that over there. Okay, now our objective is to calculate this area of the green sector. Our objective is to calculate this. Okay, an area of the green sector, let me put as x for now. Okay, so let's go one by one slowly. What is the area of the larger circle? So if you see the larger circle, if I remove my doodle here, okay, if I remove my doodle here, the area of the larger circle, since we know the slant height L is nothing but the radius of the bigger circle, which is what we have seen here also. If you open up, the green line becomes the area of this whole circle. Okay, and although it forms a sector, but this green line is the area of the whole circle. So that means the slant height is nothing but the area, the radius of the bigger circle. So hence my circumference, sorry, what I'm calculating here? Okay, we're going to talk about circumference here. Just give me a second. I think I was talking about the area of the larger circle. Okay, the area of the larger circle is this whole circle including the blue connection, and this L, which is a slant height in the cone, is the radius of the bigger circle. The whole circle, right, is the radius. So the area, we know that the area is given by the formula pi r square, but r in this case is L, the slant height, so it's going to be pi L square. Okay, and that's what we get here. The area of the large circle is pi L square. Okay, the whole circle. And on the right hand side, now we're talking about, let me remove all those things. Okay, on the right hand side, we're talking about another ratio, which is the length of the green arc. The length of this arc, like I told you, the rope, the length of this arc. What is the length of this arc? The length of this arc is going to be, when we unwrap this, this is the, we're talking about this whole thing that in purple we covered. That's going to be the length of the arc. That's from this point to this point all the way, because that's what, when you open up, that we get. Okay, and we know in the concept, this, when we in the format of cone, this forms a circle, and this is also going to have its own radius from this point to this point at the bottom. That's what we saw here. Okay, and now if you have to calculate the length of that arc, that is nothing but the circumference when the cone is formed in the circular shape, which is given by 2 pi, and whatever is the radius. Circumference is given by 2 pi, and the radius in this case is the capital R at the bottom, and that's what we get here, 2 pi r, and divided by the circumference of the whole circle. Whatever is the whole circle, again 2 pi, but the whole circle's radius is nothing but a slant height, which we already figured out, and hence we put 2 pi L. So that's kind of slightly confusing, but hang on, in a minute it will be clear. So let me repeat it for a split second. We're taking the ratio of both the areas, the green sector and the ratio of the green sector, a chopped portion of the circle and the whole circle, and we know that ratio is going to be equal to the length of the chopped portion divided by the length of the whole circumference, and that's what we are getting it here. And when we cancel out the common thing and manipulate it, we get the area of the green sector, which is what we are calculating, the x part. X part is going to be pi into r into L, pi into r into L, where this r is nothing but the radius of the bottom, which takes a circular shape, and this L is nothing but a slant height, or you can also think, when you unwrap it, it's the radius of the bigger circle if you complete it completely. That's what it is. Okay, slant height. And if I substitute the slant height formula, this formula over here, you can get this. But in a lot of exam questions, they give the slant height directly, you can apply it. But if you have to calculate in this formula also, you can calculate using the Pythagoras theorem. So that's what we have on surface area of the cone. I know I took a longer route to explain, but this is important instead of mugging up. If you want to mug up the formula, it's very simple. Just say, like I said here, pi into both the radiuses. What are the both the radiuses? One is the bottom and one is the slant height. You can mug up that. Now continuing our episode on calculating the total surface area. The only difference total circle area is, like I showed you, at the bottom we are imagining in the curved surface area, we imagine the bottom is open, the cap is open. But let's say I seal the cap with a circular shape of this sort. We put a solid object and we seal the cap. Now the curved surface area is this portion in purple color. Okay, we already calculated that above. This is pi into r, which is this r, into L, which is nothing but the slant height, L, which is nothing but the radius of the circle if this would have been complete. Now for the whole surface area, I need to just add this piece. This piece is already in circular shape. If I close it, if I close the lid at the bottom, this is a circular piece, and the area of a circle is nothing but pi r square, the radius square, and the radius of this is the same thing. It's going to be common in both the cases, not the slant height but the radius, and that's how you get it here. Total surface area is equal to curved surface area, which we have calculated, plus the area of the base circle, which is what we are calculating in the orange. We are going to take that radius. That radius and this radius are the same. The r is same in both the cases, and this gives us pi r square. And we can take the pi r common, and then we can just get L plus r. You can remember this as left plus right, if that helps you remember the formula. Okay, pi r into left plus right, and this is also right only, the right value. Okay. So basically using both the radius in a way, one is the slant height and one is the actual radius of the smaller circle. That's how you're using it. So that's kind of the wrap up on the surface area, both curved and total surface area. Again, if this helps you not memorizing the formula, but you can have an intuition, it's great. If you can memorize, it's okay, but in case in exam you don't recall, just quickly think about what was the explanation, how do we calculate it, and you will know that surface area of the cone, simply pi and both the radius multiplied. One of the radius is slant height, and total surface area, you just add the bottom, which is again a pi r square, and add it. So that's a whole perspective on the cone, and that should be a wrap up on complete topic on cone, and we'll get into some problem solving later in the next topic.